Hello everyone. Now we are going to discuss about the semiconductor laser, and the semiconductor laser we are using gallium arsenide laser. It is a homojunction diode laser. Coming to the construction of it, it is a heavily doped PN junction diode, and that heavy doping, that is the N region, it is formed by doping with tellurium, and N region it is formed by doping with zinc. And we have taken a single crystal of gallium arsenide. The doping concentration will be in the order of 10 power 17 to 10 power 19 dopant atoms per centimeter cube, as it is a heavily doped diode. And the top and bottom surface of the diode, it is well metallized to facilitate the biasing condition. And the front and back surfaces, which is perpendicular to the junction of that diode, it is roughened to avoid the lasing action in that direction. And the other two surfaces, it is well polished, and that is going to act as an optical resonator, and they are well polished, through which the laser beam is going to come out. And this PN junction, the thickness of this PN junction will be in the order of 1 micrometer. So this is about the construction of the diode laser. We have taken gallium arsenide. The P region, it is doped with zinc, and N region, that is doped with tellurium. So coming to the working of the diode laser, if we take at thermal equilibrium, the Fermi level is going to be uniform across the junction. And because of heavy doping, if we consider it is a heavily doped diode, because of that, the holes that occupies the energy levels in the valence band, so it pushes the Fermi level within the valence band. Same way, in the N region, as it is heavily doped, the electrons will occupy the energy levels near the conduction band. So it pushes, we can say, because of heavy doping, it pushes the Fermi level into the conduction band. The Fermi level, it is nothing but it is the highest occupied energy level at 0 Kelvin. The Fermi level, it is nothing but the highest occupied energy level at 0 Kelvin. So in P region, because of heavy doping, the Fermi level lies within the valence band, whereas in N region, the Fermi level lies within the conduction. It will be pushed into the conduction band. Now, when the diode is forward biased, the electrons from the from the N region enters into the junction. Same way, the holes from the P region enters into the junction region. The junction region is called the active region. That is where the recombination is going to happen. So when the diode is forward biased, the electrons enters into the junction. Same way, the holes from the P region will enter into the PN junction. So during this, a spontaneous that is recombination of electrons and holes takes place, and it results in spontaneous emission of photons. And as you increase the current through the diode, across the diode, so when the current reaches its threshold value, large concentration of electrons from the N region enters the junction. Same way, large concentration of holes from the P region enters the PN junction. So if we see at the junction region, the electrons will be occupying the conduction band, and the holes will be occupying the valence band. So this results in the population inversion here. That is, the electrons are occupying in the conduction band and there are vacant sites in the lower energy level, that is in the valence band. So population inversion occurs. So at this stage, some spontaneously emitted photons will trigger the electrons in the conduction band to transit down to occupy that vacant site. So there will be a recombination of electrons and holes that is taking place. So this is the stimulated process. Some spontaneously emitted photon that is triggering the electron in the conduction band across the junction to transit down to the lower energy level, that is in the valence band. So this recombination of electron holes is a stimulated process. So this stimulated electron hole recombination, it produces a coherent radiation that is also in IR range of wavelength 0.8 micrometer. So this is how the semiconductor laser works. That is, when you increase the current through the diode, when it reaches the threshold value, the electrons enters into, more number of electrons enters into the PN junction, and same way more number of holes from the P region enters the junction. So recombination of electron hole takes place due to some spontaneously emitted photons. Some spontaneously emitted photon will trigger the electron in the conduction band at the junction to occupy the vacant sites in the valence band. So during this recombination, stimulated electron hole recombination, it produces a wavelength 0.8 micrometer, a radiation of wavelength 0.8 micrometer. So this is how the diode laser works. Thank you.